Bottled water, specifically what's actually in it, has haunted the bottled water industry for the last 5 years, with a specific statistic repeated in headlines, infographics, and casual conversation until it became accepted wisdom. You've almost certainly heard it. The average person eats a credit card's worth of plastic every single week. It's a visceral image. It suggests that if you put your diet on a scale, you're consuming 5 grams of solid polymers every 7 days. It implies a massive physical intrusion of industrial materials into the human body. But this statistic is mathematically flawed. It was based on early, rudimentary data that prioritized mass over count. It assumed that the microplastics we consume are large, heavy plastic particles. The reality, uncovered in January 2024, is different. And in many ways, it's far more complex from an engineering standpoint. You're not eating a credit card. You're drinking a suspension of microscopic dust that has dissolved from the infrastructure of the modern world. New research using Stimulated Raman Scattering microscopy, a laser technology that didn't exist a decade ago, has recalibrated our understanding of the bottled water supply chain. We used to think a liter of bottled water contained a few hundred plastic particles. We now know the number is closer to 240,000 nanoplastics. This discrepancy between hundreds and hundreds of thousands reveals a failure in how we've historically measured industrial purity. We were looking for boulders, so we missed the sand. Today, we're going to dismantle the credit card myth and replace it with the data from the Columbia University and Rutgers University study that utilized stimulated Raman scattering microscopy, a technique co-invented by Dr. Wei Min in 2008. We'll look at why the reverse osmosis filtration systems designed to purify your water are actually the primary source of polyamide plastic contamination. We'll examine the mechanical violence of twisting a polypropylene cap against PET bottle threads. And we'll explain why the FDA is currently unable to regulate this issue. There's currently no federal standard for microplastics in bottled water, no legal limit, no required testing threshold. This isn't a medical warning. This is an analysis of how a product designed for purity becomes a delivery mechanism for the materials of its own construction. To understand the current crisis of measurement, we first have to understand the origin of the 5 grams claim. In 2019, the World Wildlife Fund commissioned a report from the University of Newcastle in Australia. They aggregated data from 50 different studies on microplastic ingestion. Their calculations suggested that through water, shellfish, and salt, humans ingest about 2,000 particles a week. To make this number tangible for the public, they estimated the weight at 5 grams, roughly the mass of a standard credit card. The American Chemistry Council and various independent researchers immediately flagged this as an overestimate. The density of plastic varies, the size of particles varies. To reach 5 grams, you would need to be consuming relatively large, heavy shards of plastic. If you were actually eating a credit card a week, you would likely notice it. You would feel the grit. The industrial reality is much more subtle. The problem with the 2019 data wasn't that it found too much plastic. It was that it was using analog tools to measure a digital problem. Researchers were counting what they could see under standard microscopes. They were limited by the resolution of their optical equipment. They could see microplastics, fragments ranging from 5 millimeters down to 1 micrometer. But the supply chain doesn't stop breaking down at 1 micrometer. Physics continues to operate at the nanoscale. This brings us to the breakthrough at Columbia University in early 2024. A team led by biophysicist Dr. Wei Min and chemist Nixin Qian didn't just look closer, they used a different method of interrogation entirely. They employed stimulated Raman scattering microscopy, the same technique Dr. Wei Min co-invented in 2008. Instead of just trying to see the particle, this technique uses 2 lasers to vibrate the molecules within the sample. Different chemicals vibrate at different frequencies. By tuning the lasers, the researchers could make specific types of plastic ring, like a bell. This allowed them to identify nanoplastics down to the nanometer scale, billionths of a meter. When they turned this technology on standard, off-the-shelf bottled water brands, the results were staggering. They didn't find 325 particles per liter, which was the standard estimate in 2018. They found an average of 240,000. 90% of these were not microplastics. They were nanoplastics. These are particles so small they behave less like physical debris and more like dissolved chemicals. They can pass through the intestinal wall, they can traverse the placenta. They don't just sit in the digestive tract. They enter the systemic circulation. But the most critical insight isn't the number, it's the specific chemical composition of the plastic they found. If you asked a layman what kind of plastic is in a water bottle, they would say PET, polyethylene terephthalate, because that's what the bottle is made of. And indeed, the researchers found PET. This makes sense. Heat causes the bottle wall to shed material. However, PET was not the most common plastic found in the water. The most common plastic was polyamide. You know this material by its commercial name, nylon. There's no nylon in the bottle body. There's no nylon in the cap. There's no nylon in the label. So, where does the nylon come from? This reveals the central irony of modern water processing. The nylon comes from the purification filters. Companies use reverse osmosis and advanced micron filtration to strip water of bacteria and minerals. These filters are massive industrial membranes made of, you guessed it, polyamide plastic. The water gets forced through these plastic membranes at incredibly high pressures to remove biological contaminants. But the friction of the water rushing through the filter acts like a microscopic sandpaper. It shears off billions of nanoscopic nylon fragments, which pass directly into the finished product. The mechanism designed to purify the water is the mechanism that contaminates it. The industry has successfully removed the bacteria, the algae, and the dirt. But in doing so, they've replaced biological impurities with synthetic ones. The purity you're buying is a trade-off. You get sterile water, but you also get the debris of the sterilization equipment. The second most common plastic found was polypropylene. This points us to another mechanical failure point, the closure system. The bottle body is PET. The cap is polypropylene. These are two different materials with different hardness ratings. When you unscrew a fresh bottle of water, when you break that tamper-evident safety ring, you're performing a violent mechanical act. You're grinding hard plastic against hard plastic. The torque required to crack the seal creates shear stress on the threads. Studies have found that particles of PET plastics can be broken off by repeatedly opening and closing the cap. The Columbia study suggests that a significant portion of the polypropylene nanoplastics found in the water gets generated at the exact moment the consumer opens the bottle. The debris falls from the cap threads directly into the liquid immediately before consumption. This recontextualizes the concept of safety seals. The seal protects the water from external tampering, but the act of destroying the seal creates internal contamination. The packaging isn't a passive shell, it's an active participant in the chemistry of the beverage. What's most unsettling about the Columbia data is what they didn't find. The researchers calibrated their lasers to look for 7 specific types of common industrial plastics: PET, nylon, polypropylene, polystyrene, PVC, and others. These 7 types accounted for roughly 10% of all the particles they detected in the water. The other 90% of the particles were unidentified. The researchers refer to this as dark matter. They know it's there. They can see the particles scattering light, but they don't match the chemical signatures of the 7 standard plastics. This suggests that the bottled water supply chain is introducing materials that we haven't even begun to categorize. These could be additives, lubricants from the bottling machinery, release agents from the mold, or breakdown products of the plastic that have chemically altered due to heat exposure. We're drinking a chemical soup where we can only identify 1 out of every 10 ingredients. This brings us to the regulatory vacuum. The FDA regulates bottled water as a food product, but FDA regulations are built on known variables. You test for E. coli, you test for arsenic, you test for lead. There's currently no federal standard for microplastics in bottled water, no legal limit, no required testing threshold. The International Bottled Water Association has responded to these findings by stating that there's no scientific consensus on the potential health impacts and no standardized measuring methods. Technically, they're correct. There's no standardized method because the technology to see these particles was effectively invented this year. The regulatory framework operates on 1990s science, while the detection technology has moved into the quantum age. However, California has begun implementing microplastics testing requirements, creating the first state-level regulatory momentum in this space. Meanwhile, the FDA issued a statement in 2024 saying that current evidence does not demonstrate that these levels pose a risk to human health. This is a carefully calibrated bureaucratic phrase. Does not demonstrate risk is not the same as demonstrate safety. It simply means the data is too new to form a conclusion. However, the medical community is beginning to generate that data, and it's moving faster than the regulators. In March 2024, the New England Journal of Medicine published a landmark study that moves the conversation from what's in the water to what's in the body. Researchers examined the arterial plaque of patients undergoing surgery for cardiovascular disease using pyrolysis gas chromatography mass spectrometry. We know plaque builds up in arteries, causing heart attacks and strokes. What we didn't know is what that plaque is made of. They found microplastics, specifically polyethylene and polyvinyl chloride, embedded within the fatty plaque of 58% of the patients. This is a crucial data point. It confirms that plastic doesn't just pass through the digestive system like corn. It gets absorbed, it migrates, it lodges in the lipid deposits of the cardiovascular system. The study found that patients with plastic in their plaque were 4.5 times more likely to experience a heart attack, stroke, or death in the following 3 years compared to those with plastic-free plaque. We must be precise here. This study shows correlation, not necessarily causation. It doesn't prove the water caused the heart attack, but it proves that the materials of the supply chain, the polyethylene of the bottle, the PVC of the pipes, are physically present at the site of the medical failure. The biological system treats the plastic like cholesterol. It sequesters it in the vessel walls. This forces us to look at the bottled water industry not just as a beverage provider, but as a major tributary in the global flow of synthetic materials. Global production of plastic has exploded from 2 million tons in 1950 to over 400 million tons today. Bottled water drives a significant portion of this volume. The US market alone hit 47 gallons per capita in 2021. We're producing containers that get designed to be used for 20 minutes and then exist for 400 years. But the nanoplastic research shows us that the bottle doesn't wait 400 years to break down. It begins to disintegrate the moment it gets made. The credit card statistic was a clumsy attempt to visualize this flow. It focused on weight, which is the wrong metric. A credit card is a static object. What we're dealing with is a cloud. When you hold a bottle of water up to the light, it looks crystal clear. That clarity results from the reverse osmosis and the micron filtration. It results from removing everything that reflects light in the visible spectrum. But if you could see in the vibrational spectrum used by the Columbia researchers, that bottle would look very different. It would look like a snow globe. You would see a suspension of hundreds of thousands of nylon fragments from the filters, polypropylene shards from the cap, and PET degradation from the walls. You would see the entropy of the logistics network trapped in the liquid. The engineering consistency ensures that this particulate profile stays uniform. Whether you buy the water in New York or Los Angeles, if it went through the same filtration housing and uses the same cap design, it carries the same nanoplastic load. So, how does an observer of industrial systems navigate this? First, recognize that the credit card myth was actually a minimization of the problem. It framed plastic as a foreign object you could spit out. The reality is that nanoplastics are a systemic component of the water itself. You can't filter them out at home because they're smaller than the wavelength of visible light. Second, understand that purified water is often more processed than tap water. And in the logic of nanoplastics, more processing equals more contact with plastic machinery. The more filters the water passes through, the more opportunity there is for shear stress to generate nanoplastics. Tap water, by comparison, typically flows through larger pipes and sand filters, involving less high-pressure friction against polymer membranes. Studies indicate tap water contains significantly lower counts of nanoplastics than bottled varieties. Third, watch the regulatory space. The UN plastic treaty negotiations have stalled repeatedly. INC 5 in Busan, December 2024 deadlocked, and INC 5.2 in Geneva, August 2025 adjourned without consensus. The geopolitical friction over plastic production mirrors the friction in the bottle cap. There's immense economic pressure to keep the plastic flowing. The industry argues that without standardized testing, we can't regulate. The science argues that we can't wait for standardization to acknowledge the contamination. The bottle in your hand is a marvel of logistics. It allows you to hydrate safely, anywhere in the world, without fear of cholera or dysentery. That's a triumph of engineering. But that safety comes with a material cost. We've traded biological bacteria for synthetic nanoparticles. We've traded the risk of immediate infection for the long-term accumulation of polymers in our tissues. The water inside the bottle is H2O, but the liquid you're drinking is a mixture of water and the system that delivered it. You aren't eating a credit card, you're drinking the machine.